Good morning, good afternoon, and good evening, wherever you're tuning in from. My name is David Lakatos. I'm the Chief Product Officer here at Formlabs, and I want to talk to you about what it means to create bleeding-edge products. As you may know, Formlabs started about 11 years ago, and we set out to change 3D printing by making it super accessible. 11 years ago, we went on Kickstarter, and we did something amazing. We brought Form 1 to the market with two very simple materials, gray and clear. These were materials that got you started in prototyping, but they were very simple, just to get you started. Over time, we released more advanced products, like the Form 1 Plus, alongside with more advanced materials, like clear and black, and also flexible, our first functional material. Later on, as our hardware has developed even further, we added products like the Form 2, and we added more functional and engineering-specific materials like tough, high temp, and our first biocompatible dental SG. We started seeing an explosion of interest from different industries, so we added more functional materials, more specifically for applications and niches. These more and more tailored to specific needs for our customers. Over time, we went into dentistry, the medical industry, or jewelry that required our formulations to either be biocompatible, adhere to a specific application, or be very good at casting, for example, for jewelry. And we kept on doing this as we added the third line of the product, Form 3, and also the Form 3L, the larger format printer. And this continued all the way through last year when we added our first selective laser sintering printer and product line with the Fuse 1. We added Nylon 12, Nylon 11, really groundbreaking materials for the selective laser sintering market. All the way up until this year, we kept on adding new materials, but just this year, we released 3 new materials, and I want to really jump in to talk about these because these really mark a different era when it comes to our product strategy. Specifically, I want to talk to you about polyurethanes and our PA11 carbon fiber materials. But before we do that, I just wanted to highlight how I'm excited to see all of you here today. If we would be in an arena with tens of thousands of our customers all in one place, if you would look to your left or to your right, most likely you would see somebody totally different than who you are, from a different industry, working on different applications. And this is one of the most exciting views for me. We see a plethora of different type of applications, different type of customers, both in the prototyping and more in the end-use parts world. When it comes to dentistry or medicine, all of our parts are actually being used in procedures, which is really, really cool to see. But we're seeing more and more applications also on the end part used from other industries, and we'll talk a lot about our collaboration with Hasbro recently that we're super proud of. And all of this allowed us to sell more than 100,000 of our printers and help you build more than 100 million parts. And I'm super proud of this. But what I want to talk to you about today is not where we succeed, but where we come short a lot of times. Because 3D printed materials, as you all know, often still do not measure up to the thermoplastic counterware parts that you're printing or getting from other methods of getting parts to you. And all of you would have experienced brittle materials, where the elongation was too low and your parts broke. Or like this shovel here that should not have been so bendy, it should have been a straight handle. It crept over time and deformed over load. Or discolored material that just comes from UV exposure. This is not great news for us, this is not great news for you. We need to be doing better, and we want to invest more into these new materials. The number one reason when we talk to you for turning away from 3D printing as a whole is because you don't find the material that you want to print on. Formlabs is one of the very few companies that is not just working on materials or just software or just hardware. We're working on the entire ecosystem because the material doesn't work without the software, and the material and the software need to be tailor-made for the hardware itself. We know that we need to do this because without more capable materials, we're going to get stuck. We're not going to be able to really change the industry according to our ambitions, and we need to really want to make an impact on the scale of manufacturing as a whole industry, not just rapid prototyping or niche applications. One of the things that really exemplifies this is the current state of affairs in selective laser sintering market. If you look at what all of you are using, not just on our machines, but on other competitor machines as well, it's pretty much all PA12. That means to me that there is not enough available materials for all of you to use that is tailor-made for your applications, and everybody's kind of using the same thing. We are changing this very rapidly. You can see that just in the 1 year that we have been in the market, we're approaching more than 50% of all of the units shipped in this market are Formlabs machines. So we are the ones that are going to make an impact here, and we're very excited to do so. Our ambitions are very high. And this is what will allow us to really expand access to digital fabrications so we can really deliver on our mission, which is we want to help you make almost anything. To me, this really means that if you are a customer that wants to make parts, you think about Formlabs. And we're doing it because it's hard, and we know that this is the way that we're going to get to our long-term goals. So we need to be the ones that are creating industry-leading materials that are durable, they're stable over time, that are aimed at these high-performance applications that the materials today are not able to get to. Often these are going to be end-use applications. And we need to figure out a way to make that happen, not on super expensive application-specific hardware. We need to be able to figure out how to make it work on the printers that we already ship today and are in the hands of tens of thousands, hundreds of thousands of people. What we're going to do today is look at two materials that we released in the last 6 months, PU Rigid, Polyurethane Rigid 650, and P11 carbon fiber. These two materials represent enormous, dramatic changes to the material properties that are out there. They innovated, whether it's tensile strength, elongation, or impact strength, a huge amount on what's possible today. But they do require a little bit of extra work. And it really exemplifies our overall approach to the market. What we want to figure out is marry the accessibility, the low cost, the affordability of some of these cheaper entry-level printers and the very, very high performance industrial machines. This is what we did with the Form 1 first when we got to the market. And this is exactly what we want to do with these materials as well. We want to take industrial processes like urethane casting and marry the powerful performance of urethane casting with something like the ease of use of a standard 3D printing materials that you already love and use today on your Formlabs machines. That's kind of the intersection that we're going after. So let's start with PU Rigid 650. Why are we so excited about it? We're excited because it is a material that, kind of, if I'm comparing it to durable, has a comparable tensile modulus, which kind of compares to stiffness, but it has dramatically higher elongation, which means it can just perform a lot better. It will not break that easily. It has a impact strength, which is notched isod, significantly higher than durable. So you can drop it, you can exert forces on it, and it will not break. And it has a higher heat deflection temperature, which means longer thermal stability. It also means lower creep, so you can put load on it, a higher temperature environment, and it won't deform as much as durable. And it's able to flex back and forth a huge amount of times before it breaks. You can use it for circuit boards, consumer electronics, automotive shock absorbers, and a variety of other applications. But again, it's a very impact resistant and pliable material. But why is it different to use? So I want to kind of put it into context with our Formlabs standard materials. Formlabs standard materials do not require any additional equipment. You just buy the printer. Yes, you can buy additional post-processing equipment, but you're not required to. It's optional. The post-processing workflow is a wash, and then for the standard materials, it's actually an optional post-cure. We design these materials that you don't even need to post-cure it if you don't want to. We recommend you do because you get better material performance, but you don't have to. And pot life, it's something that we don't even talk about. These materials, unless you expose them to UV light, they remain liquid, and until their expiration date, you can use them, which is usually years. If I compare this to polyurethane 650, the picture changes a little bit. You need a dry cabinet. So these are very, very special materials, and they use a dual cure function in order to reach these much higher properties. First, it uses the same UV curing, as you already know from our standard materials. We use UV light to kind of give it a form, but then we use humidity to get to that much higher functional property that differentiates them from the standard materials. In order to do that, we put this humidity sensitive material into a dry cabinet. You can see there on the right. You print in that. Once you print it on it, you transfer it into the humidity curing oven. This is how you kind of control the humidity, the lack of it to be able to print, and with humidity at the end, humidity chamber to lock in the properties. You need to wash it twice with a PGDA solvent, which is an alternative to IPA, and then you need to cure it for a couple of days, depending on the thickness of the material in the chamber. The pot life of this material is not forever. Even in ambient conditions, even in the dry chamber, after weeks, it will cure. So that's what we call pot life. But I wanted to juxtapose that to a more traditional or an existing 3D printing polyurethane printer. which is a two-part system. So out of the gate is worse from that perspective. We are able to ship our material. We spend a lot of time on not creating a two-component material, but the ability to really ship one canister that you can then use. So the competitor has a two-part system. You need a $150,000 plus machine to start printing. You need a mixing and metering machine to be able to deliver these materials from the containers into your resin tank. You need a centrifuge to post-process it. You need a $20,000 to $30,000 washer system to be able to post-process it, and then you need to put it into an industrial oven. Lots and lots of steps. The post-processing workflow is metering and mixing, centrifuge, 2 washes, and then bake for days. The pot life also is only hours, which is really problematic, especially if you're trying to print out a larger part. Here's the competitor printer's print. So again, this is a $150,000 machine, and you can see it on the top of the print. It wasn't able to finish. The pot life was so short that during the course of this print, the material went from a liquid to a solid, and it became unprintable. This just showcases you some of the issues that some of these higher performance materials can have. We have engineered around this. We have a longer pot life, and you're able to print for a longer period of time. But again, this is kind of the industry standard until we came to the market. All right, so what we're going to do now is go through a print. I want to show you how this part was printed on our machine, what were the steps, and show you how it's done. All right, so printing with PU. So this is one key difference. You're pouring in the resin manually to be able to start a print as quickly as possible. I'm using a Form 3L inside of this dehumidifying chamber, putting it into the build platform, and we'll start the print right after. After I come back, a couple hours later, I have the part ready, taking it out of the dry chamber, and you can see printed very nicely. And I'm going to be using a form washout to post-process this in PGDA, which is an alternative to IPA. I will do this twice actually. I'm not going to show both of them, but I'm going to use 2 of them. Here I'm using compressed air to get some of the residue resin off the platform. It's very easy to remove from the build platform. And the consistency is kind of like a very thick chocolate that has been dried a little bit. And after I remove the supports, I will put it into the humidifying chamber. And after a couple days, I take out the part, and I have it here with me. So here is the nice lacrosse head. We actually mounted on a lacrosse stick as well. So you can kind of see the application, and we are going to be testing out how tough it really is. Before I go forward, I want to tell you that we have a real material science team here. 50 people and lots of very fancy equipment to do real ASTM tests. But sometimes, I think for demonstration, it's much easier to show how part breaks. So we're going to be dropping weights onto these parts. So we're going to use, first of all, benchmark our Formlabs PU Rigid 650. We're going to test a standard gray part just to show you how they perform against our standard parts. We're also going to use a industry standard FDM machine from Stratasys and their ABS M30 material. We're also going to use another PU material from a company called Carbon and their polyurethane resin. Finally, we're going to test it to an epoxy hybrid material from Somos, the Somos Towers. And we'll go into the danger zone to go for the testing. All right, so it's time to break things. So what you see here is our experimental setup. What we're going to be testing here is impact strength. We're going to be dropping this weight from different heights onto a part in a roughly consistent orientation. Again, before I get any comments or angry emails, this is not how we test our materials. We have a very professional materials team. I'm barely a physicist, closer to an electrical engineer, so I don't know what I'm doing, but our materials team does, and they have their real equipment that they do ASTM testing on, so this is just for demonstration. But this is way more fun. So let's start with an ABS part. So this is an FDM ABS part. I expect it to break rather easily, so I'm going to just start it from roughly the first mark here, and it broke. So you can see that this is a relatively brittle part, and it was able to break without any larger height. We printed this from a service bureau from Stratasys. Let's get on to some more performant materials. All right, second experiment. This is a Formlabs gray material. Again, we expect it to break relatively easily. This is not a material that we created really for breakage. So 3, 2, 1. It was quite satisfying. All right, so this one is a competitor polyurethane part. Let's see how much. I think this will need a little bit more oomph. So we're going to start from the third mark roughly. And did not break. Let's see if it breaks from the fifth one. All right, this broke it. Cool. All right, this is a competitor hybrid epoxy part. I think this is going to take a little bit more, so I'm going to start from roughly the third mark. It didn't need that much. Well, so much for impact strength. All right, so moment of truth. We're gonna make this interesting. Instead of just testing our part, we're going to be using an R650 that was submerged for more than an hour in an ice cold bath. It's nice and chilly. So this should really show you that if it can survive after being cooled down for an elongated period of time like this, it should really show you that this is a super performant material that you can put out into the elements. So let's try it from third height. All right. Oops. That's nice. Survived. So let's go a little bit higher. Let's go up to about here. Still in one piece. All right, let's try from all the way up. All right. So, good news is that our R650, even after cooled down for over an hour in ice cold bath, it was able to survive. It was exposed to a lot of force. You can see it deform a little bit, but otherwise super nicely intact and ready to use. And in fact, we have a lacrosse stick that is all laced up and ready for action. I do not know how to play lacrosse, but I heard it's something like this. And you can see that this is actually a real part. The part was designed by one of our Formlabs employees called Josh Bass. And I believe he actually plays with us. So, on to the next material. All right, this was fun. Love breaking things. Let's go to our next material. So, I want to talk to you about our first carbon fiber material, Nylon 11 carbon fiber. It prints on our Fuse machine. It has chopped carbon fiber in it, and that's what really creates a much differentiated, dramatically different material properties than anything that we have on the market today. It's great for tools, jigs, fixtures, cases, housings, anything that really requires a lot of durability and lightweight. This is a visual way of looking at material properties. So what you see here is all of our material for SLS, plotted 7 different material properties. And these material properties are some of the most important ones between elongation, HDT, tensile strength. What you can see here is that the light gray one, the largest in area, that's Nylon 11 carbon fiber. While a larger number doesn't always mean better properties, you can see that this is a dramatically different material that has kind of a higher performance on each of these axes compared to any of our other materials. And that's, again, because of the chopped carbon fiber that is inside of these materials. I know that this is an eye chart. Don't worry about all of the numbers. The thing that I really wanted to make sure to highlight is that while the superior material properties are very nice, this is a very different material than any of the other materials, nylon 12, 11, and nylon 12 glass-filled that we have on the market. You can see that there are 3 columns below nylon 11 carbon fiber. And that's because this material is anisotropic, which means that there's a difference in material properties depending on the direction that you're measuring from. And that's because of the carbon fibers. Carbon fibers are axis aligned when we're going through with the roller inside of the fuse. We're aligning all these carbon fibers in a specific way. Because of that, you get the highest tensile strength in the x-axis, while the y and the z have a drastically different material property to them. This means that it's a different material. It is higher performing for sure than the other materials, but it requires a little bit more careful consideration how you're setting up your print. So how is this different in use? Again, you need to be designing for anisotropy. In Y and Z, you have a different material property than in X, and you need to be thinking about how you orient your parts. If you're printing a bracket, if you're printing something that requires strength in a specific direction, make sure you know which way you're going to be putting that into the build chamber of fuse. The second one is that it does have carbon fiber in it, and it can cause some skin irritations, so gloves are required for comfort and safety. We try to be generally very universal when it comes to the safety of our products and make sure that we don't put a lot of limitations onto the customer. But for these higher performance materials, we do have some advanced safety requirements, and that's something that you need to be aware of. So let's go through printing. What you can see here is a Fuse 1 Plus that I'm using with the PA11 carbon fiber. I just finished the print. Build chamber has a bunch of brake calipers in them. I'm transferring over to Fuse Sift, and once I lock it in, I will be able to start ejecting the parts from it. So far, it's very similar to what you're used to. We need to be careful. I'm wearing just a normal kind of dust mask, KN95 mask, while I'm doing this, and here I'm just breaking the parts out of the cake, and after a little bit of brushing action, I will be able to get a roughly clean parts that I will be able to transfer to a 12 box where I can use compressed air and media blaster to get to my final parts. That's what I'm doing here. You will be able to see how I'm post-processing these parts using just a standard media blaster and compressed air. And we're back. This is the PA11 carbon fiber part that we've printed on the Fuse 1 Plus. And we're going to be testing this against 3 other materials. One of them is a Stratasys industrial FDM machines M30 ABS material. We're also going to test it against a Markforged Onyx carbon fiber part, and then finally another FDM printer's carbon fiber filled material. So we're going to go ahead and start breaking these parts. This is our experimental setup. We have a force measurement device here that is connected with a 3D printed part to basically the plank that I'm standing on. I'm going to be exerting some force on this part, and we're going to use a slow-mo camera to tell us exactly how much force was exerted before it broke. And by that, we're going to look at its tensile strength. So let's get started with the Stratasys ABS M30 material. All right, so this first part broke around 90 newtons or so. Let's go to the next one. All right, next up, we have a carbon fiber FDM part, carbon fiber nylon FDM part. Let's see how this does. All right, this one fared a little bit better. It took me about 120.5 newtons to break it. All right, So this is the Markforged Onyx, also an FDM carbon fiber filled material. So let's see how much it can take. We measured 83 newtons on this one, and we actually did it a couple of times. I'm surprised how low this was. Definitely a finicky material to make sure that you're oriented right, but I definitely was expecting more. Finally, we're going to use our Fuse 1 Plus part here, printed on P11 carbon fiber. Let's see if I can break it. Definitely 2 hands required. Okay. Chris, can you come and help me, please?
Oh, you broke the handle.
All right. I guess that will have to do for today. So good news is that our part is still intact. Even with Chris's help, I was not able to break this chain. However, unfortunately, we did rip our handle. So the largest readout that we got was 950 newtons, so significantly larger than any of the other parts that we have tested. And hopefully that shows you that these parts really have an incredible capability when you pay attention to which direction you're printing with it, to account for the anisotropy of carbon fiber 11 parts. But I hope you can use this in your next application. Well, this was a lot of fun for me. Hopefully it was for you as well. I just wanted to wrap up by saying that for us, really, the focus is increasing accessibility. We want to create powerful, easy to use, affordable printers so we can take all of this added value and this added performance that I demonstrated today to as many people as possible. We're not interested in just giving this capability to a couple, 10 or 100 customers. We really want to expand this industrial quality to a much larger group of people. So we can really be the one-stop shop that you come to when it comes to any problem that has to do with making parts. And we want to help you make anything. Thanks for listening, and I hope you enjoy the rest of the day.